Hello, friends. We're continuing our study of geometry. Today, we're going to do lessons 14 and 15. Again, I'm following the Saxon textbook, but lesson 14 is so short. It's one quick point that I'm going to combine 14 and 15 together. 15 is a little bit longer, but that's okay. Here's lesson 14. It's another one of the logic lessons. We've already talked about the idea of a conjecture, right? A conjecture is a statement, it's an idea. So we see a pattern and we make like a statement that sort of sums up what we think the pattern is going to be. So, for example, one conjecture would be that you can find a new prime number by taking two prime numbers, multiplying them, and then adding one. Okay, there actually is something like that, but I'm modifying it a little bit because this conjecture doesn't work. But here's an example. Someone might get this idea because they're thinking and they're like, well, 2 times 3, 2 and 3 are both prime numbers. And if you multiply them, you get 6. And when you add 1 to that, then you get 7. And 7 is another prime number. So maybe if I just take any two prime numbers, then I can multiply them together, add 1, and I get a new prime number. So how do we disprove a conjecture? Right? You can either try to prove it or you show the pattern over time. But all you need to disprove a conjecture is what we call a counterexample. I think I mentioned it in this lesson, but here the textbook's introducing it formally. One counterexample disproves the conjecture. So in this case, the counterexample is 3 and 5. If you multiply 3 and 5, right, so 3 times 5 is 15. Now, 15 plus 1 is 16. And that is not a prime number. So what we just went through here, this is the counterexample to this conjecture. Okay, and that's basically the whole lesson, just this idea that we disprove a conjecture using a counterexample. Now, we're going to move on to lesson 15, which is just a slide this way. So lesson 15 is all about polygons. We're introducing the idea of a polygon. You're probably familiar with this before. I'm sure you've done it in elementary geometry, but we're going to give, again, some technical terminology, some technical definitions to these things so that we can, again, build our way up, and things are going to get more complex as we go along. So polygon, the word polygon actually means many-angled. Um, poly comes from Greek meaning many, and we have a lot of roots in English like that. None come to mind at the moment. Um, Polyphony, right? Many sounds. Um, and then gon comes from the Greek word gonia, which means angle. So, a polygono is a many-angled figure. Interesting, though, we define a polygon as having many sides. But of course, if you have a bunch of segments that are making up sides, then of course you're forming angles. So a polygon would also be something with many sides. The Latin for angle is just angulus. And so polygon in Latin would be something like multi-anguli. And you see there's a mix of Latin and Greek in here. We'll get to that. So technically, a polygon is a closed figure of 3 or more segments. If you only have 2 segments, how would that work? Um, and so, 3 segments would be a triangle. And then, so these are examples of polygons. They could be any shape, but as long as it's only straight lines and they all connect back together, a closed figure, that's a polygon. These are not polygons. The one on the left here has a curved line, so that's not a segment. It doesn't count. And the one on the right is open. It's not closed. So that is not a polygon, the technical way we define it. Okay, now a regular polygon is equiangular and equilateral. I mentioned this when we introduced the idea of the equiangular and the equilateral triangles in the lesson on classifying and naming triangles. And so this is that, right? Equilateral, equiangular. A equiangular and equilateral quadrilateral would be a square. Very familiar figure to you. But again, to simplify it, because we're kind of lazy, and we don't like to have to say equiangular and equilateral. It's a mouthful. So we just say regular. A regular polygon, uh, all the angles and all the sides are congruent to each other. So regular. So according to the regulus, according to the rule, an irregular polygon is not both equiangular and equilateral. So it could be equiangular, like a rectangle, with just extended longer sides. One pair of sides is longer, but this is not a regular quadrilateral. It's not a regular polygon. because it's not both equiangular and equilateral. This thing is neither equilateral or equiangular. The one on the right is a rhombus. It's got all equal sides, but the angles are not congruent to each other. So that is an irregular polygon. Okay, some other kinds of polygons, or no, so now naming polygons, how we name them, based on the number of sides. Again, a little strange. Gonia is the Greek for angle, but it all fits together. So an n-gon has n sides to it. So if you get to like something with a lot of sides, it's got 15 sides, you can call it a 15-gon if you don't know the name, right? So the technical name for a 10-sided figure is a decagon. But let's say you don't know that, you can just write a 10-gon. Um, and so, but of course, that's accepting triangle and equilateral. So triangle and equilateral, we're using Latin. And then once we get beyond that to something like a pentagon, 5 sides, penta and gon, those come from the Greek roots, right? Hexagon, hexa means 6, so it's 6 sides. Octagon, 8 sides like octopus, right? Comes from, again, the Greek for pods, meaning foot, right? So it's an 8-footed creature, lives in the ocean. The ocean doesn't come into the name of it somehow. But anyway, diagonals of polygons. Segments that connect two non-consecutive vertices. So the vertex is a corner, basically, right? If you were to just connect two consecutive, so consecutive meaning like ones that are next to each other, or one follows from the other. Again, consecutive, con meaning with, and secutive comes from the Latin sequor, which means to follow, right? We see it in words like sequence. And so consecutive means one after the other, it follows the other. So non-consecutive means that you're kind of crossing over from one to another vertex that's not right next to it. And so these are two examples of diagonals. There are only two diagonals in a pentagon, right? And you've got 5 sides and 5 angles. There are only two diagonals that you can draw. All the others, if you went here to here, that's just tracing a side. From here to here is also just tracing a side. Okay, so a lot of vocabulary, right? Polygon, the names of the sides. What does it mean for a polygon to be regular? What's a diagonal? But again, it all matters because we're trying to form this really tight, logically, perfectly coherent system. So we got to make sure everything is right on point here. Get that points because we're talking about geometry. Anyway, convex polygon. All diagonals are interior. So it's convex. What it means is there are no caves, right? I think it's better. Let's talk about what a concave polygon is. This is an example of a concave polygon. Uh, Basically, it has a cave, right? At some point, you're going into the polygon. So there's this cave-like part to it. If it doesn't have any cave-like part to it, then that means you have a convex polygon. But one way of talking about convex and concave polygons is referred to the diagonals. Um, in a convex polygon, like this one that we were looking at before, you can tell all the diagonals are inside of the figure. But for this one, for this concave polygon, if I go to draw um, some of the diagonals, watch what happens going from here to here. The diagonal actually goes outside of the polygon for a little bit. And then these two, if I connect from here to here, the two leftmost vertices, I'm actually completely outside. That is a diagonal of that figure, but it's completely outside the figure. So another important uh, pair of vocab words, convex and concave. Again, pretty simple, but it all matters. Congruent polygons, very simple idea, simply that two polygons that have the same shape and the same size. So all the corresponding sides are congruent, all the corresponding angles are congruent to each other. Okay, and then last concept in here, interior versus exterior angles. So here's a figure, quadrilateral and irregular quadrilateral. And the interior angles are basically the angles on the inside of the polygon. Real simple, right? So angle AMH is this interior angle. Angle MHT is this interior angle. An exterior angle is formed by extending one of the sides. When you extend one of the sides, what you get is an angle here that is outside of the polygon. And that's called an exterior angle. By the way, little note. Notice that this angle here, MHT, and this angle here, THE, these two angles form a linear pair. and therefore they're supplementary. So the interior angle and its corresponding, its adjacent exterior angle, they're always supplementary to each other. And that's the note here that I put in green. So thanks for watching. Don't forget to like and subscribe.